Good morning everyone, I'm Mr. Ish. Thank you for joining me for this video. We're looking here at a quick part 2 video for the same subject matter that I presented directly preceding this video. The simple concept of a derivative. You know, in that video we showed you how this concept of derivative can be easily understood, especially when you look at it with regards to this perspective. If you have 2 points here on a curve or a function, draw a line between those 2 points. You have a secant line. When you determine the slope of the secant line using this formula, you end up getting an average rate of change. But when you modify this line such that you bring in a limit as h approaches 0, so you're bringing the second coordinate and bringing it right on top of this x, the original coordinate, such that the 2 points, point 1 and point 2, are coincident, and now you draw a line. It happens to graze the curve at that point, and you end up seeing a tangent line. When you determine the slope of that tangent line using this formula, this right here is basically called the basic definition of a derivative. When you analyze that tangent line using this formula, you end up getting the instantaneous rate of change, which tends to be more important than the average rate of change, because it tells you with regards to your model what is happening to your analysis or your model, whatever it is that you're studying at a particular point in time. However good this explanation process is with regards to some student learning the derivatives, because this is how you learn derivatives, this is what you are introduced to first, this equation form right here. But however good it is, this equation form does have a limitation, and I'm going to spend the remainder of this video just showing you that limitation. The limitation is this: for all but the most easy or basic forms of functions out there, this procedure becomes rather cumbersome when you're trying to use this formula over here to determine a derivative of a function. And I'll show you just a single example, and then we'll wrap the video with that. The single example that we will look at now is the same function from the video preceding this one. We saw this one, 1 over 2 e to the power of x over 10. We were utilizing this hypothetical function for that practical example involving the population growth of a specific bacterium. If you are to calculate the derivative of this, you know you have 2 procedures. You can use a template for an exponential function, which is the best and most advisable procedure because it's easy. The second method is to use a basic definition of a derivative to do this. If you were to use this template method, it's very fast, and you know you have to use a chain rule. And we'll quickly breeze through this first one, then we'll take some time in the second manner by which we can solve this derivative. You know, if f of x is equal to that, then you know the derivative of f of x is equal to, and we have to calculate it. You can push 1 or 2 aside. If u is equal to x over 10, then function with regards to u is e to the power of u, and you use a chain rule. You have e to the u, and then du dx, you have x over 10. When you do all of this to completion, you know it's not hard. You'll have 1 over 20 e to the u, but u was x over 10. And here your derivative factor has been completed. And this, if you were to put a value for this x, you would get your instantaneous rate of change. And this right here is an easy procedure. And there's nothing wrong with you learning template techniques for any of the functions out there, because this is the recommended way of doing it. To use the other definition, the basic definition of a derivative, that way of doing it is cumbersome for a function like this, but it can be done, and I'm going to show you. But prior to showing you, you have to understand this single assumption, that is how the derivative of anything which looks like this yields you this. Because you've seen this, you know, when you look at something like this, the derivative template is this, and you should be able to show why this is the case, because this learning how to do this procedure comes in handy when we're doing the basic definition of a derivative for this function. Let's quickly do it. If y is equal to e to the ax, you can bring in the natural logs and take your equation as this: ln y equals ax, but ln e is just equal to 1. You can erase this. Now you can do implicit differentiation over here. When you do that, you'll have dy dx 1 over y is equal to a. The derivative of x is just a 1, so it disappears. And then you solve for dy over dx, which is the same thing as y prime, or derivative with respect to y. You have seen this before, and that's equal to a to the y. And you resubstitute what y was, which is this, and you have a e to the ax. So here we've shown you that this template can be very easily derived without using or knowing what the template is for an exponential function derivative. The exponential function derivative has this template, but if you didn't even know this, you could derive it using this procedure. You have to keep this procedure in mind in the back of your head when we look at the same function over here using the basic definition of a derivative. So the procedure proceeds in the following way. If that's your function, the derivative of that is equal to limit h approaching to 0, you gotta hit this with that 1 over 2 e x over 10, and you'll do x plus h over 10 minus 1 over 2 e x over 10. all over h. See, f of x plus h minus f of x divided by h. You can push the 1 over 2's out and you can do everything like this. 1 over 2 has been pushed out, limit as h approaches 0. You have e to the x plus h over 10 minus e to the x over 10 all over h. You see how this process is a little more cumbersome, but it's still doable. You have to use the laws of exponents and simplify what you see. You have limit here as h approaches 0. This can be split into e to the x over 10 plus h over 10. You see how I split this common denominator into its separate parts. Minus e x over 10 all over h. This right here can be rewritten using the laws of exponents. When you have the two bases being similar, the exponents add. So this is no different than you saying e to the x over 10 times e to the h over 10. Think about it. You have two simple bases here, similar bases, their exponents should add, and you'd get that. Now you can isolate something over here. So you'll have 1 or 2 sitting out here. You have limit as h approaches 0. You have to isolate e x over 10 because it's found here and it's found over here. And then you have this separation which occurs minus 1 all over h. Now something is beginning to take form. You see 1 over 2, you have limit as h approaches 0, you have e x over 10, and then you can actually create a new limit as h approaches 0. You have all of this part right here, e to the h over 10 minus 1 over h, and you have to evaluate these separately. You have a 1 over 2 sitting out, and we will do it all here in one step. Limit as h approaches 0, e to the x over 10 remains as e to the x over 10. But this right here has to be handled using the L'Hopital's procedure, because think about it, if you put zeros in places of these h, you get an indeterminate form of 0 over 0. You'll have a 0 in the numerator, 0 in the denominator, and you'd have to use the L'Hopital's procedure. You do the derivative with respect to h in the numerator, and you do the derivative with respect to h in the denominator. And this is why I showed you that little derivation procedure, because anytime you would do the derivation of this, in terms of the derivatives, here you basically have something which looks like e a to the h, which you know in terms of the derivative procedure would be a e to the ah, because I've shown you this and I've derived this for you before we even started this procedure. That would be in the numerator. The derivative of the 1 is just a 0, the derivative of h is just a 1. So everything here with regards to the L'Hopital's procedure, numerator and denominator undergoing the derivative procedures, will just yield you this 1 over 10, which is your a exponent right here. It's 1 over 10 times h, 1 over 10 e to the h over 10 all over 1, and this is being hit with a value of 0, which you can plug directly in places of h. Now we are very close to being done. When you plug this 0 into places of h over here, you have e to the 0, which is just a 1. E disappears as 1 in the denominator disappears. All you're left with is just a 1 over 10. This 1 over 10 can multiply with this 1 over 2 sitting outside. You have 1 over 20. You can open up the parentheses and you get e to the x over 10, and you end up getting your derivative factor, into which you can plug in a value for x for whatever it is, and you can get your instantaneous rate of change. But you see, using the basic definition of a derivative for a non-traditional function like a quadratic or a simple radical, but now we're going to the realm of trigonometrics or hyperbolics or exponentials or natural logs. When you do the basic definition of derivative, it becomes cumbersome, which is why the template schemes are all the much better. But the basic definition of derivative is very useful in that it helps you understand the basic and the simple derivative concept. You apply the templates only to simplify the actual derivative procedures, and I've shown you this over here. Perhaps the hardest part in all of this is to apply the separation over here, and then to remember to do the L'Hopital's procedure over here because of an indeterminate form coming into play as h approaches 0. And then you take everything through to completion and you're done. And that's all I wanted to show you in this video. Thank you for watching. Have a nice day.